Okay, so let's start talking about the way we're going to combine functions. Combining functions is very useful because we're able to generate new functions based on the previous one that they're given. For example, if you think about if you know a function that represents the cost of producing something, and you know the function that represents all the revenue that you get, or all the money that you get from selling these products in this company, then the difference would be the profit function. So this is something that is very useful. It allows us to find new values in a very short amount of time. But let's just start with the concept about how we're going to be able to combine functions. The same idea that we were adding numbers. For example, 3 plus 4 gives me 7. If I have a number and I add another number, then the answer gives me another number. So the same idea here with functions. If I have two functions and I add them, the result is going to be a different function. The same applies for different operations, differences, products, and quotients. I can add, I can subtract two numbers and get another number. I can multiply two numbers and get another number, and I can divide numbers and get another number. So the same is going to happen with functions, but the result will be a different function. So let's say that I don't have the formulas for f and g, but I do know how they change certain values. I know that f changes -2 into 3, -1 into 1, 0 into -2, 1 into 0. Remember that this will be the input values, this will be the output values for f. And let's say that there's a function g that changes -2 into -1, -1 into -1, 0 into 3, and 1 into 2. For g, these are the input and this is the output. I don't have formulas, I don't have a rule for f and g, but I know what f and g do to these particular values. So I can graph these functions into a coordinate plane so that you can distinguish between the two of them. I marked f, the dots with the x's, and I graph g as just the dots. So you can see both of them are functions. They pass the vertical line test. So let's talk about what would f plus g look like. A function that is defined as f plus g. First of all, f and g have to have the same inputs, otherwise this is not something that you can do. So I notice that f and g have in common -2, so that is an input that is allowed to have. F and g also have -1 in common. F and g also have the 0 in common. F and g also have the 1 in common. So I'm able to find what is f plus g. Now f plus g will be simply the function f evaluated at that value plus the function g evaluated at that value. Since f of -2 is 3 and f of -2 is -1, so this is just simply 3 plus -1, which is 2. For -1, f is 1 and g is -1, so I'm going to add those two and that gives me 0. For 0, f is -2 and g is 3, so -2 plus 3 equals 1. And for 1, f is 0 and g of 1 is 2, so this gives me 2. So then I'm going to be able to graph this. -2, 2 will be the point to graph for this one. -1, 0, 0, 1, and 1, 2. So now we just plot the function, not f, not g, but the function f plus g. And also, as you can see here, if this is f of -2 and this is g of -2, what happens when I add +3 to -1? I only get 2 back. What happens when I add +1 plus -1? I get 0. 3 plus -2, I only get 1 back, and 2 plus 0, it remains as 2. So graphically, as well as with the tables, I can verify that the f plus g is correct. Now, what would be like to have f minus g? Well, it's the same idea. I have to verify that I'm working with the same axis, but instead of adding the y values, I'm going to subtract, because that's exactly what it says, f minus g. So this means subtracting the y values. And in here, this will mean adding the y values. So we're going to do that, and I'm going to have, it says f minus g, so you do have to respect the order. F of negative 2 minus g of negative 2. So that means the 3 goes first, minus negative 1, and that would be 4. So 1 minus negative 1, that would be 2. Negative 2 minus 3, that will be negative 5. And 0 minus 2, that will be negative 2. And this is something that I can graph as well. For negative 2, now I have 4. 1, 2, 3, 4. For negative 1, I have 2. For 0, I have negative 5. So that's going to be over here. And for 1, I have negative 2. And this is the graph of f minus g. This is my x-axis, my y-axis, if you haven't seen that. Now, what would it be like to have f times g? Again, I have to verify that they share the same x values, which they do. I don't have to verify that. Again, and now I'm going to multiply the y values, because that's what multiplication means. So it's 3 times negative 1, that's negative 3. 1 times negative 1, which is negative 1. Negative 2 times 3, which is negative 6. And 0 times 2, which is 0. So I can graph that again. Negative 2, negative 3 will be right here. Negative 1 will be right here. 0, negative 6 off the graph, but that's okay. And 1, 0 is right here. So this is the graph of f times g. And lastly, I can also divide. So f divided by g will be this table. And then I have to make sure that the x values are the same. And now I'm going to divide 3 by negative 1, which is negative 3. 1 divided by negative 1, which is negative 1. Negative 2 divided by 3, which is, well, negative 2/3. And then 0 divided by 2, which is simply 0. So I can graph that as well. It will be here, and then negative 1, negative 1. 0, negative 2/3 is over here, not quite negative 1. And 1, 0 is here. And that's the graph of f divided by g. So as you can see, f plus g, f minus g, f times g, and f divided by g produces different graphs. And it doesn't look at all as f or g separately. Like, this is something that the result is going to have to depend on what the numbers are. But let's say that I were to say that f and g are continuous. So f will look like this, g would look like this, but then these shapes are not repeated in any of these graphs. So that's just a comment on that. This is just the way we're going to define the functions. If you're adding two functions, that's just adding one plus the other. And the domain of this function is going to be the intersection of both domains. And the idea is that you can always find what the addition of two functions is, as long as the input of f and the input of g intersect, meaning that whatever x you're evaluating has to be present in both of them. So this is intersection of both domains. For example, let's say that you have these two functions to combine. So remember, g is a shift to the left 3 units, and it would look normal. So this is g, and then in here you can see really where it went until you factor this. So I know that 2 minus 6 is the same as the opposite of x minus 2. And now you see where it went. It went to the right 2 units, and then it was reflected over the y-axis, so it looks like this. So that's what f and g look like. In here, the domain of g will be from -3 to infinity because it goes from here over there. And then the domain of f will be from negative infinity up to the number 2. From negative infinity up to the number 2. So to be able to combine f and g, I have to pick x's that are in the domain of f and in the domain of g. So for example, if I were to pick negative 5, this is something that I can find f for, but I can't find g of negative 5. So to do f plus g of negative 5, that will be something impossible. So I'm going to show you the same idea in the following app that I found online. So if you Google function of operations GeoGebra, this is something that you can access online as well. I didn't do this, this guy over here did it. And it has the functions that I just told you. F is the square root of 2 minus x, and g is the square root of x plus 3, and you have them graphing here. So let's say that I have x equals negative 3. Oops, sorry. X equals negative 3. So you can see f of negative 3 is 2.24, and g of negative 3 is 0. So to have f plus g will be to add those y values, and that will be right here, this function at negative 3. This is the coordinates is negative 3, 2.24. And I can do the same for negative 2. For negative 2, f of negative 2 is 2, and g of negative 2 is 1. So when I add 2 plus 1, that gives me 3, as you can see over here. And then for negative 2, f plus g is 3, and that's the point that it generates. So I can do that for all the x's that I want. So negative 1, that will be over here, and so on. But what happens if I pick negative 5, for example? As I said, well, you can see it here. Let me put another one. Let's say 5. So for example, for 5, g of 5 is something that I can find, but f of 5 does not exist. Therefore, if I'm trying to find f plus g, 5 is a value that is not the domain of f plus g. F plus g is only defined for all the x's for which f and g are defined, both of them at the same time. So as you can see here, if the domain of g is from negative 3 to infinity, and the domain of f is from negative infinity up to 2, the intersection will be all the x's from negative 3 to 2. These are all the x's that f and g are defined for at the same time. So for this function to be able to graph, it is only going to exist between negative 3 and 2. For the subtraction of two functions, I can subtract them, and the domain is still going to be the intersection of both domains, or all the x's that belong to both domains. For the multiplication, the domain is going to be still the same. But now for the division, the domain is going to be all the x's in the intersection, as long as g of x is not 0. Because it is in that point where you really can divide by 0. So for example, in this situation, f plus g will have domain from negative 3 to 2, as we can see, and so does f minus g, and f times g has the same domain. Now for the division of f divided by g, g cannot be 0, meaning square root of x plus 3 cannot be 0. So for what value of x g as a function is not 0, that value is x equals negative 3, because when I replace here, x plus 3 is 0, square root of 0 is 0, so this cannot happen for the division. So I have to exclude out of this domain that I'm suggesting, I have to exclude negative 3. So since I have to exclude them, then it won't be a closed interval at negative 3, it will be an open interval at negative 3. But 2 is not a problem, so 2 remains closed. So in here, I'm taking away that value that makes g 0 because I don't want it in my domain because it cannot be defined. So for example 1, remember that f plus g is suggesting that we are going to add the y values. Now, since it says f plus g, but it doesn't say f plus g of 2 or 3 or -5, this implies that it's going to be in general for any x. So the function f, if the input is x, what does it do to x? Subtracts it by 2 and finds the reciprocal. And the function g, whatever it does to the input, is just takes the square root of the input, and that's how the output is. So I'm trying to find what is f plus g of any x of any value, and that equals, well, if you give f of an input x, then it's going to do that. So I just write it out. And then I'm going to add what g does to anything that goes in, which is square root of x. And then that's it. I added two functions. And in here, there is nothing else that I can simplify. I could add these two, this algebraic fraction with this square root, but I know it's not going to go anywhere. It's not like I have 1 over x minus 2 plus 1 over x plus 1. I know how to do these, and I would know how to do that too, but I know it doesn't go anywhere. It's not like I'm going to have a polynomial on the top or on the bottom, so it's okay to leave it like that. Now I have to find what the domain is. Now the domain, it's going to be the intersection of both domains. So the domain of f, there is no problem with f as long as, since it's a fraction, then the denominator cannot be 0. So the domain of f is all the x's such that x is not 2. Okay? And the domain of g is, remember, if it's a square root, I cannot take the square root of a negative number, so x has to be positive or 0. All the x is such that x is positive or 0. Or you can write x different from 2, and you can write this as interval from 2 to infinity, from 0 to infinity. That will be okay too. Now, what is the intersection of these two? If this is something that you don't see in your head, it's okay. You can draw the number line on the side and see what the intersection is. And this is why we practice this skill on the previous sections. The domain of f is everything but 2. So this is the number line. I have the number 2 right here. So for f, I can use every single x except for 2. So at 2 is open. The domain of g are all the positives including 0. So g is using from 0 and all of them. So the part of the number line that gets shaded twice is not this part, but it's from 0 and on, except for the number 2. So the domain of f plus g would be from 0 to 2 open, union from 2 to infinity open. This is excluding 2. It's open at 2. That's what it means. Okay. Other way you can write it, you can say x is bigger than or equal to 0, less than 2, and 2x is bigger than 2, less than infinity. You can say that as well. Either way, it's fine. Now, this will be the same domain for f minus g. It will be the same domain for f times g, and it will be the same for f divided by g, as long as we make the denominator different from 0. So let's figure out what f minus g is. F minus g equals 1 over x minus 2 minus the square root of x. Since g doesn't have any other terms, I don't have to use parentheses. But if g had other terms, then I'm forced to have parentheses there. In the domain, it's the same as the one that I found before, from 0 to 2, union 2 to infinity. F times g, it will be 1 over x minus 2 times square root of x. Now if I think of this as a fraction, I just have to multiply across. This is the square root of x over x minus 2. And the domain, and the domain of f times g is the same. It's from 0 to 2, union 2 to infinity. And now f divided by g of x, 1 over x minus 2 divided by square root of x. And remember, when I divide, that's the same as multiplying by the reciprocal. I like to write it this way because I know how to multiply fractions very easily. I can just multiply across. When I divide by this and I have a fraction, then it gets a little confusing. So always change it to multiplication by the reciprocal. And now I just multiply across. So this is 1 times 1 is 1, and then square root of x times x minus 2. Remember that this is a quantity, so when I'm multiplying two quantities and the second quantity has two terms, you have to use parentheses. It would be a mistake to leave it without parentheses. So now let's talk about the domain. The domain is of f divided by g. It's going to be the same domain as before. You just have to watch for g being different from 0. G is square root of x. Square root of x different from 0 means x is different from 0. So since x cannot be 0, it cannot be close at 0. So I'm just going to open it at 0. And then everything else is the same. I just took away x cannot be 0. And this is like a cloud because I already wrote that here. X cannot be 0 because divide by square root of 0 means dividing by 0, and that can be done. Okay, and now this process is gonna get quicker and quicker the more you practice. So don't think that it's gonna take us 10 minutes to do every problem. I'm just trying to think out loud and the things that are going through my head when I'm doing that. But once you get used to it, then it will be a piece of cake, I promise. Now part B says find f plus g of 4. So in this case, it's not of any number. It says in particular of 4. So the only thing you have to do is, since you already figured out f plus g for any number, you just have to plug in 4. So f plus g, I'm going to do b here. F plus g of 4 means 1 over 4 minus 2 plus the square root of 4. And that's 1/2 plus 2. And that's 2 1/2. Done. F minus g of 4 will be 1 over 4 minus 2 minus square root of 4, and that will be 1/2 minus 2, and that will be negative 1/2. Done. F times g of 4 would be 1 over 4 minus 2 times the square root of 4, and that will be 1/2 times 2, and that will be 1. And then f divided by g of 4 will be 1 over 4 minus 2. You can either divide by square root of 4, or as I suggested, you can multiply by the reciprocal times 1 over square root of 4, and this is 1/2 times 1/2, and that would be 1/4. And that's it. I promise I'm almost done, but if you want to go and have a snack, this is a good time to do that. After pausing, of course. It says, using graphical addition. The graphs of f and g are shown in figure 1. Use graphical addition to graph the function f plus g. So g is growing at a constant rate, and that's okay. And f, I noticed that it grows or increases and then decreases and then increases and then decreases. And then f plus g, how would that look like? Well, definitely not as a straight line, because I know that the y's for f are changing. They grow and they get smaller and so on. So I just want to mark some important points on the graph of any of these. G is straight, so really there is nothing interesting there. But since f is wavy, I know that I have some interesting points here. There is some local maximum minima that I can focus my attention on, and I have the endpoints. I know where f begins and I know where f ends. So those are going to be my important points. Now, for every x, I want to be able to find what f plus g is, meaning for every x, I want to be able to find what the sum of the y's looks like. Since I can't do that for every x because there is infinitely many x's here, I want to find out for the x's that are right here for f. So I'm going to focus on only 1, 2, 3, 4, 5 values of x. How does that f plus g look like? So in here, for this x 0, f is 0, and g is that much. So I'm going to use my spaghetti. The height under x equals 0 for f is 0, and for g is this much. So I'm going to split my spaghetti. I hope this works. Okay, so that's how tall g is when x is 0. So f plus g just looks like g. Now for x equals 1, this is how tall f is when x equals 1. So let me just split it right there. Oh, a little bit taller than I wanted it to, but you get the idea. Can you stay there? Okay, thank you. Now for g at x equals 1, that's how g is. That's how tall g is when x is 1. So I have this here. If I'm adding f plus g, then I'm gonna put one after the other. So that's how tall f plus g is. Now I need my pencil. Man, I need more hands to do this. That's how tall f plus g is for 1. Now for, I mean, not 1, I didn't mean 1. I don't know what that x is. For this x of 1, okay? For this is x of 0, this is x of 1, another value of x, another value of x, another value of x. I don't know how much those are, honestly. I mean, there's no scales. And it really doesn't matter. I'm just doing a sketch of f plus g. So for x of 2, that's how f looks like. Now this is going to be a challenge. I'm going to have to use my teeth. But I just had them done, so I don't think I can. This is way too much, but you get the idea. I have f there, and then g of x sub 2 is taller right there. So when I add those two together side by side, that's what I get. F plus g, ladies and gentlemen. And then, oh, look at that, I can reuse that piece, kinda. For x sub 3, this is how tall f is, and this is how tall g is for x sub 3. And then when I put them one after the other, that's the way to say I'm adding f plus g of x sub 3, and it's up here. And then for the last one, maybe I'm reusing this one. I'm a genius. What would you do without me? Okay. And that's how big g of x sub 4 is when I put it side by side. F plus g. Go away. Okay, f plus g. And it's over here. So now you have, whee! That's a very good one. I think it's better than the one that you have on your book. If you go back to your textbook, there is an answer to that. So I have used graphical addition. For any particular x, you just visualize how tall the function is at that particular x, how tall is the function at that particular g, and add one on top of the other one, and that will be a good sketch of that. So I use a spaghetti. You can use a spaghetti if you want, you can use a piece of paper if you want, you can use a ruler if you want, but the idea is that for any x, I'm adding the heights, how tall the function is at that particular x on top of the other, and that's all.